Welcome to the second part of the lectures. Today I will talk about the basic of radiations. So for radiations, so there is environmental radiations in the nature. That means we are some sense exposed by these natural radiations. And also radiation is used particularly for the medical application and industrial applications. There was those aspects of the radiations. And as you know, sometimes it's harmful to human health. So there is many aspects of radiations. However, in the, for example, news, in the media, this part is sometimes, almost always, emphasized. And this aspect, natural radiation and application, but not well known. So the purpose of this lecture is that I'm trying to give you some scientific information about radiations, and I want that this information will be useful to the scientific understanding of the radiations. Okay, let me begin with what is this radiations. So this picture shows the constituents of materials, for example, the water. And as you know that water is made of H2O molecules. That molecule are made of atoms. And atoms inside, there are nucleus and electrons, and even that nucleus made from nucleons, protons and neutrons. And for some occasions, these constituents are emitted from these particles or atoms or molecules. If this happens, we call that radiations. And there are several types of radiations are known that we said that alpha ray, beta ray, gamma ray, or X-ray. These three types, alpha, beta, gamma, almost cover the type of radiation. However, that when the nuclear reactions, for example, in the nuclear power plant, that phenomena or facility is related. The neutron is sometimes emitted. Okay, let me begin with that alpha ray. This is actually a nucleus of helium atoms that made of 2 protons and 2 neutrons. When that nucleus of helium atoms are emitted, we call that alpha ray. One important feature of this alpha ray is that we can stop it with a piece of papers, very thin piece of papers. Then beta ray, actually this is electrons. Electron is that, for example, electric current is that if the electron move inside the metals, we call that electric current, and it's the basis of the many kind of electric phenomena related to our lives. Then that electron is emitted from the some materials. We call that beta ray. And beta ray penetrates through the paper, but it can be stopped by the relatively light metals, aluminum, for example. And gamma ray and X-ray. I think that X-ray is that most famous radiations. if we visit the hospital or clinic, so we sometimes take X-ray pictures to look into the inside of our bodies. So many people are familiar with these names. That X-ray penetrate papers, aluminum, but it can be stopped by the iron or lead bricks. Then neutrons. So we usually do not see this neutron. But for example, that neutron is radiated, emitted through the reactions called nuclear fissions or nuclear fusions. So that neutron penetrates paper, aluminum, iron, lead. Then to stop these neutrons, we use the water or concrete, denser concrete, for example. So this is a type of radiations. So there are several types of radiation, and each has its unique features. Then another point related to the radiation is there's some word or unit that are sometimes confusing. Okay, so let me talk about the radiation and radioactivities. There are materials that emit radiations. We call that radioactive substances. That materials emitted radiations, alpha ray, gamma ray, beta ray, usually. Then radioactivity is that how much radiation that radioactive substances emitted. The unit is becquerel, BQ. Then 1 becquerel stands for that 1 emissions per second. So radioactivity is that ability that radioactive substances emit radiations. Then these emitted radiation, in some occasions, hit human body and absorbed inside the human body. Then if this radiation coming outside from the outside of the human body, we call that external exposures. Then how much energy was absorbed or deposited inside the human body? That is absorbed dose. And its unit is called Gray, GY. Actually, this is absorbed energy, joule per kilogram in human body. And the other occasions, we could take that radioactive substances with a food or with air. Then in that case, we took the radioactive substances and we exposed by the radiation from the inside of our body. That is called internal exposures. So there's 2 types of exposures by the radiation, external and internal. Then another feature we usually use is that half-life or half-lifetime. The radioactivity is not constant over time. That decreases with time. And the time or period in which the becquerel down to 1/2 is called half-lifetime. It looks like this. That really depends on radionuclide. I listed some of the half-lifetime of the typical radionuclide. For example, 131 iodide, this is 8 days. 134 cesium, that is 2 years of the half-lifetime. However, look this, 40 potassium, this is 1.2 billion years, very, very long. That half-life times really depend on radionuclide. Some is more than billion years. Some of them is days or even less than 1 second. Then another unit we heard for the news, for example, is that sievert. That sievert, SV, is a measure of the impact on human health. That is a sievert. So to estimate the sievert, we have to begin with the gray absorbed dose. So if we encounter some absorbed dose in the unit of gray, we have to take into account what type of radiation, alpha ray, beta ray, gamma ray, or neutrons. So there are some factors, that is called radiation weighting factor, that stands for the impact of human bodies. So beta, gamma is 1, the alpha is 20. That it means that with the same gray absorbed dose, the impact on human body is from the alpha ray is 20 times larger than those of the beta ray or gamma rays. Then that is called equivalent dose in the unit of sievert. That stands for the effect to each organs. Then effect of entire body is estimated by the effective dose. Again, that unit is the sievert, SV. In this case, from this equivalent dose, now we need to take into account which organs we have the exposures, dose, lung, or stomach, liver, for example. And depending on these organs, there are some factors. Then taking into account all these factors, we could estimate the effective dose. That stands for the effect of radiation to human body, entire bodies. So in short, to estimate the impact to human body, human health, that is expressed by the sievert, that take into account types of radiations and types of exposures, where or internal or externals. Okay, this is a unit we usually use for the radiations. So next step we have to consider is that how we can evaluate, how we should evaluate the effect. For example, if we exposed by 1 millisievert, for example, so it is a serious, or it may not be serious, give a serious impact to human body. To consider that effect, one thing we have to know is that there is radiations around Earth or our daily life. So this table shows that element in the Earth's crust. So number 1 is oxygen. That is not radioactive, and its abundance is 0.46. That means the 46% of the Earth's crust is made of the oxygen. And the second, silicons. So oxygen and silicon is number 1, number 2. This is because the materials made from this oxygen and silicon is SiO2, that is rock. That means the Earth's crust is made of rocks. Then number 7, abundance is 0.0121, that is potassium. potassium is an essential nutrient. For example, we have to take a vegetable in order to take the potassium, for example. Then small portion, 0.0117% of potassium is what we call that potassium 40, and which emit gamma rays. So which means that we have the potassium 40 inside that emit gamma ray. So we exposure by gamma ray from this potassium 40, or in other words, each human emit gamma rays from potassium 40. Then other radioactive element is that 39 thorium, 51 uranium. Maybe the uranium is that most famous radioactive element. So this has a radioactivity. The one point I would say is that 69 and 71, it's a helium and gold. They are not radioactive. However, that if we average over Earth crust, thorium and uranium, abundance is larger than this helium and gold. So you could imagine that there was a radioactive element inside Earth, and that's not very rare. Then this is an example how we find radioactivity around us. Potassium 40 is on the ground, inside the ground. Then that emit gamma ray or electrons, beta ray. But this potassium was took into vegetables. And we have vegetable. In this way, we took potassium inside our body, and that emit gamma rays. And the other example is that 210 polonium that emit alpha rays. Then this polonium was included in the fishes. Then Japanese people takes more fishes than world average. That means that the Japanese people was exposed by this alpha ray from the potassium more than the world average. That is one point. The other example is that uranium. Uranium is a metal. Because it's metal, it's inside the ground, inside the rock, Earth's crust, and stay there. However, that after several radioactive decays, that become the other radioactive element, radon. And radon is a gas. Because it's gas, sometimes it's going to the air, like this. And we took radon with air. Or sometimes it's going to the water, underground water. And if that underground water was heated up, it becomes hot spring. And it will be a radon hot spring. This picture shows the natural radiation in Japan. The difference is mostly coming from the difference in the rocks, soil in Japan. So you see that the east of Japan and the west Japan, we see some difference. So that shows that the land or soil of Japan is different for east and west. Actually, west of Japan, we see many granite comparing with the west of Japan, and that granite include the potassium, and that emit gamma ray. That's the reason why we see the red and yellow in the west of Japan, more than the east of Japan. Okay, then taking into those effects, what happens if we sit in a room, in the apartment? So there is a gamma ray emitted from the walls, because if you live in the concrete building, the concrete made of sand, rocks, that emit gamma rays. And also, there are radon in the air. We took that radon from the air. So that is always happening when we are living inside the rooms of the apartments. So then, this is the other type of radiation. That is radiation from space. We call that cosmic rays. So radiation is always coming from the space, but our Earth, or surface of Earth, is protected by air, dense of air. So this cosmic ray did not hit Earth's surface directly. However, that something remains. In typical surface of Earth, the cosmic ray, we see that the particle called muons, that's a kind of elementary particle. There's a 90% of cosmic ray on the ground surface is muons. The other 10% is electrons. For example, that in this palm, the area is about 100 square centimeters. There's 1 muon hit this area per second, always. So this is a picture that how much radiation we got when we took a plane. When I go to the Tokyo in the business trip, I'm taking a flight from Hiroshima airport to Haneda airport in Tokyo. At that time, I took a portable dosimeter that measure the gamma ray radiations. Then yellow point is a number measured by this dosimeter, and this green is a flight level. So we see this is where I was in the Hiroshima airport, and after takeoff, it's going up because of the cosmic ray, and the cruising altitude almost same. Then descending to the Haneda airport, that decrease, and you see that this is a very lower point, because you may know that just before landing the Haneda airport, we fly over the oceans. Above the ocean, the radiation is a little bit small. Gamma ray radiation is a little bit small. Then, after landing on the Haneda airport, inside the airport, we see some radiations. And if we take a look at this picture carefully, just after taking off, it dropped down. Just before the landing is dropped down. This is because this device try to measure the gamma ray. So just after the takeoff, so we did not have the gamma ray from the ground, so it decreased. And after that, it started to increase due to the cosmic ray. And also, if you compare the radiation level in Hiroshima and Tokyo, Hiroshima is a little bit larger than Tokyo. This is, as I said, the natural radiation is a little bit larger in the west of Japan. Okay, this is a summary of the natural radiations. Orange is Japan, and green is the world average. So, food. In Japan, Japanese average 0.99 millisievert per year. This is because Japanese people have more fishes than the world average. On the other hand, radon from in the air, world average is larger than Japan. This is because Japanese people still living in wood. The house is made of wood. And in the world, mostly they're living in the rock, concrete. That made these differences. And the other, gamma ray from soil and cosmic ray, that almost same. Anyway, in the total, in Japan, average is about 2.1 millisievert per year. In the world, 2.4 millisievert per year. So if we remember these numbers, that can be a reference number. I mean that when you hear the news about the radiation from the TV or media report, so you could compare their report from this number, then evaluate that this is too much or this is really dangerous or we should be watch out. Okay, this is a summary for so far. Radiation have types and each type has characters. And in the environment, we have the natural radiations, food, air, soil, cosmic rays. Then, next point we have to discuss is that we know that this is a natural radiation, so we have to consider that effect of radiation to human bodies. And there is another type of radiation, that is artificial radiations. As I said in the beginning of these lectures, we use the radiation for the medical and industrial applications. So in order to understand this, including these applications, we need to understand the effect of the radiation to materials, including human bodies.